Then let's move forward, right? Now we have talked about all the this hand waving thing. Now I also want to do some equation. You might feel very boring at the beginning. Looks like a lot of equation, but our equation is basically these few weeks. I try to review. But the most important is the intuition. You see, I keep repeating some concept, right? I hope that you can memorize those concepts and have the intuition. Okay, so what is Poisson equation? Again, if I write it down, you don't need to memorize, right? This is Poisson equation. It looks very complicated for you, but don't worry. I don't ask you to memorize. But basically, this is a 3D. It's the divergence, right? So what does it mean? First of all, what is epsilon? Can someone tell me what is epsilon? Permittivity, right? Usually it is ER times E0, right? ER, for example, silicon, ER of silicon, anyone remember? Is what? 3.9. Thank you. ER of silicon dioxide is what? I think I say something wrong. Silicon is not 3.9, I'm sorry. 11.7. Right, this is 3.9. Okay, and epsilon naught is just the vacuum one, 8.85 times 10 to the power negative 14 farad per cm. That is the first thing, right? I hope that, right, you don't have to memorize the equation, but when some people show you this equation, you understand what is epsilon. Right? Just a fundamental constant. This night when you learn Newtonian mechanics, maybe you don't need to memorize all the acceleration, but when some people give you G, then you know, oh, that is mg equal to the weight, right? Your mass times the G equal to your weight. You understand that one, okay? And of course, phi is what? Just the potential. And the whole goal of Poisson equation is to solve for the potential, right? The unit is volt, right? And then rho is the charge density. What is the units of charge density? Can someone tell me?
The coulombs per centimeter cubed.
Very good, right? So you may say meter cube or whatever, but you know that it's charge per volume, okay? I hope you have this in your mind, right? Divergence is very complicated, right? No need to remember, I just give you. Right? What is divergence? It's basically just partial xi plus partial yj plus partial z k. These are the unit vector, right? So if you have a divergent two together, it becomes this. I don't want to go into the calculus. I only give you, you even don't need to know if you don't feel like, but I hope that you can at least know what know there is such thing, right? So this is okay, but you do need to have some feeling about the one dimension case. In one dimension, this becomes partials, instead of partial, we just use d, 2d squared, dx squared, epsilon, right? Maybe let me just move it to this direction, negative rho divided by epsilon, right? This is the Poisson equation. What is the relationship between electric field and the potential? Can someone tell me? Electric field is the gradient of the potential and the negative gradient. This is something you need to memorize. right? The most basic thing in the EM is negative. Okay, so if I do this, then it also means that this is just dE Poisson equation is just like this also. Okay, so you have this form. These are the three things I hope you can. Second one, definitely you need to memorize, right? As an electrical engineer, this is almost like the grammar in English, right? If your major is English, you need to know the grammar. As an electrical engineer, you really need to tell people electric field is just the gradient of the potential times which and negative, right? Any questions about this? Now you might not get that immediately, but I hope that you can link it to the link them together, because you might read paper, read document, they talk about different things, and you know that after all it is just a complicated 3D case, right? All these vectors are very useful, very important, but they don't give you new insight. If you understand the 1D, you know 90% of the 3D. Okay, so don't be scared by people who give you the vector. Right? Just ignore them. But in your heart, you should know that what is the meaning in 1D. So why this is important? Because for the whole device physics, we are using the Poisson equation a lot. This is just the F equal to ma, right? Now, here I show a capacitor. Can you tell me what condition is this based on the charge and the drawing? Is it accumulation, depletion, or inversion? First of all, tell me what is the substrate? Is it N-type or P-type?
P-type.
P-type, because?
Fermi level is close to valence.
Thank you. Fermi level is close to valence band, so you don't have much electron in the conduction band, right? Because again, Fermi-Dirac distribution tell you that the tail is very small, so you don't have much electron there, but you do have some hole in the valence band, P-type. Okay, it is labeled already, but can you tell me, do we apply positive or negative bias to the gate? Based on how it draws the Fermi level. What can make you push down the
Positive voltage?
Positive, yeah. It is set here, right? But still from here. So this is P-type. So it's like MOS. But anyway, we put the positive gate bias here, right? So it pulled down. So now can you tell me it is an inversion, accumulation, or depletion?
Accumulation.
Okay, someone say accumulation. Thanks for answering. But let's just look back to the curve. When we do MOS, we start with accumulation, depletion, and then inversion, right? Now we actually apply a positive bias. So it is in the inversion. But how do I see that? You see that the band is bended here. So actually, the Fermi level is here. So you get more electron, right? So at high bias, positive bias, you get positive charge on the gate. Then you have the depletion, and then it has the inversion. Sorry, I don't know, I said the thing wrong. It is inversion here. Is that okay? Now, why I do this, I just say, then how are you going to find the electric field? How do I draw this figure? I draw this figure just hand-wavingly based on my experience. But in reality, you need to solve the Poisson equation, right? So we need to solve Poisson equation. First of all, let's look back. What does it tell me in Poisson equation? dE dx equal to rho divided by epsilon. This one, dE dx equal to rho divided by epsilon. I know the rho already. Rho is the charge density, right? So how do I find E? E will be equal to integrate of rho divided by epsilon dx. All I need to do is just keep integrating here. Okay? Now, maybe you're not sure this is like a delta function, right? In the delta function, when you do integration, when I go from here, 0 electric field. Once I hit here, because of the delta function, when I do integration, it jump up. Then I don't have charge here. The area is constant. Correct? And then suddenly, I see this negative charge. It will go down. And then I continue to see negative charge. It reduces the area, right? Total area, because it's negative. It go down in a straight line because this is constant. And that is how you get the integration. This one, you see Qm, right? See nothing. And this jump, you see negative Qs, right? And here, you see negative Qna. That is how you do the integration. We are not doing that, right? There's a lot of math. But as a human being, you know that is integration. You know that integration means counts the area. You will be able to draw this curve. Once I hit this one, it goes up. I hit another delta charge, I go down, jump, and then I go down slowly because of the constant charge. Right, so here, this equation brings us from here to here. Any questions? Right, I will talk about intuition more than equation. You now at this stage, even you tell me you forgot this one, it is fine because you only need to remember you integrate the charge to get the electric field. Integrate the charge to get the electric field, memorize it. Or you differentiate the electric field to get the charge. Any questions? Today, you guys are not that active in asking questions. I hope that is because it's clear to you, right? But then how do I get the potential? How do I get the potential? Again, d phi dx equal to electric field. So how do I get potential? Just integrate the electric field over distance. So now I look at this, I start integrating, right? So here we try to set something, potential you can set different level. It start with V, just the preference of the author because we put V here. Nothing, straight line integration. And suddenly you go up, but because it's negative, so it just reduced as a straight line because I see this constant. Okay? So here I will say, you go down because you see, let me just call this A. Okay? And let me call this B. Now, then you reach here, you continue to integrate this region, but integrate slower because now the area increased lower. But it is straight line, so you have a curve, it's second order. Here, you see B. So you get the potential, right? But this potential is the real potential. You then need to multiply by -1 to get the band diagram. Because band diagram is the negative of potential. So now do you see that this one straight line and then curve down, right? going down. Here you see this one goes up straight line and then curve up. We have this discontinuity because of the band gap issue. But that is how you find out the potential of this shape. It's all by integration. Right? So in summary, you get the, so there's a few steps, right? Let me say, this is step 1. You get the electric field from the charge by integration. Then you get the potential from electric field by integration. And finally, you multiply it by -1, you get the band diagram. If you have not done that before, it might be a little bit confusing to you, but we are going to do this very often in the lecture when we see different device, different bias condition. And this is the skill you need to develop, right? I won't ask you to memorize the equation, but I can just give you this initial charge profile and ask you to tell me what does the band diagram look like. Is that clear?
Professor, can you please explain the A part in the second graph again?
Oh, A part, what one? Oh, you mean how to get A part?
Yes, Professor.
Yeah. So this is like we do integration, right? And then if I don't have Qm, when I go to here, it is still 0. But why? But here we have this Qm, which is a delta function. When you integrate a delta function, if you remember, you integrate a delta function,
You get that, right?
you get 1, right?
Yes.
Okay, so once I pass this delta function, which is what? This is like, you get a delta function, but it has the magnitude of Qm, and then of course you need to also divide by this one, right? Dx. Then what do you get? You get Qm divided by epsilon. Is that okay?
Yes, Professor. Yes, sir.
And that's how you get this one. The level is, I think there's a typo here. What?
Okay, Professor. That was.
Is okay?
Yes, Professor.
Okay, this should be Qm. I think it's a typo in the book. Okay, good. Right, so that's why you get this one. Good question.
Professor, I didn't understand how you got from the that third chart to the band diagram.
You mean this part?
Yeah.
So yeah, first of all, what I'm trying to say is just times, let me say this, times the whole thing by -1 means flip it, right? So when I flip it, what do you get? You will get this potential. You will get something like this. Right? Is that okay? They flip, right? Becomes negative. And this is a straight line. And this is in the oxide. Right? So now it means your oxide. Just look at this one. This one tells you the potential. So your oxide, you have valence band and conduction band. So you just draw them in this way, right? Same slope going up. And then how about for the semiconductor? The potential is this shape. Again, you draw the valence band and conduction band. But they don't connect each other because they have different band gap. This only tells you the potential. It does not tell you where is the conduction band. It's just saying that the potential change in this way. But because of this has a larger band gap, you need to draw it like this so you have a discontinuity. But this shape, look at this one curve, is the same as this shape. Does that answer your question?
Yes, thank you.
Okay, good. Yeah, thank you for the question. I think you are helping other students also and make my class more clear, right? Any other questions?
Professor, like, do we integrate to normalize the curve from second to third?
We don't normalize. Okay, so that's a good question. We integrate, but depends on what you normalize. We adjust the reference because for potential, we only care about the relative. So you are right. If I integrate from here, I should start from 0, and then it will go down. So this becomes negative, but I shift everything up by V. So we did not do the so-called normalization, but we shift the whole curve by V. Is that okay?
Yes, Professor.
Okay. And it's your choice. Why we shift by V? Because we apply V here. So I want to start this with V. That's the only reason, right? It doesn't matter how you call it. We only care about the relative. Okay, so we need to practice this more, okay? Now let me go. Now I show you the Poisson equation again, right? Why I want to show you, just give you one piece of information. So about Poisson equation. So there's one thing very interesting. Poisson equation, right? This whole term is talking about this one. Remember the Poisson equation is the divergence. All right, you can, if you put epsilon into here, if it's constant, you have divergence square phi equal to negative rho, right? Here is, this is the rho. Okay, but in depletion region, you only have Na. Oh, maybe you kind of forgot what kind of charge we have. What charge do we have in semiconductor? Can you tell me what type of thing is going to contribute to the charge? Electron density, correct? And what else? In a region, you can have electron and you can also have what? Hole. But hole is positive, right? I start using the TCAT notation. P represent for hole concentration. What else do you have?
Fixed charges.
What charge?
Fixed
Fixed charge, very good. Fixed charge, we have two types of fixed charge, right? One is donor, ND. It is positive, right? Because they give negative electron, they becomes positive, right? This is donor charge. What else? So you say fixed charge, you're right. Two types of fixed charge. What else? Besides donor, what do we have? Can you see it now with the annotation?
Yes.
Okay, so I'm writing, right? You can see it, right? I write acceptor.
Yeah.
Okay, so now what else? Sorry, acceptor, right? Is that okay? Because your region can have donor, acceptor, you have hole and electron. And this is the rho, this is the total charge you have. In a depletion region, right? What does meaning of depletion? It means no electron, no hole. That's the first thing, right? So this is the concept I want you to have visualized in your brain. Depletion means no hole, no electron. At the same time, because it's MOS, right? I assume there is no acceptor, no donor. I will assume ND equals 0. Okay, so that's why rho is just equal to negative Na, or negative rho divided by epsilon equal to Na divided by epsilon. Here I actually missed one thing. I need to multiply this by the Q, the charge of the electron, because these are all talking about how many per unit area. So I need to multiply this by Q. Okay, and that's why here it say that on the right hand side, I should put negative. On the right hand side, it just says that in the depletion region, your right hand side is just QNA divided by epsilon, right? And this is constant in some cases. Okay, so what is the point of this? This, we might use it later or you might not, but if it is in 2D, you're basically saying that dE dx plus dEy dy equals to a constant. Okay, this will be useful for you to study, but that is something telling you that if my electric field changed by something, for example, this is the electric field. If it changed by something, the change in the x direction and the change in the y direction, when you add them together, they will be a constant. Okay, so why do I want to, this will be useful later in the SOI, but I don't need you to memorize. But however, by through this equation, you further understand what is the meaning of Poisson equation. How we get Q and A. And actually is testing you the understanding of semiconductor physics. You know that there are electron and it is negative, there are hole positive, there are ND, NA. You know that at depletion, they have to be 0. That's why you get this term. And that's how you change the Poisson equation to this. And it has a special conclusion saying that the change of the electric field component in all directions sum up to be a constant. You might not use it later, or you might, but just an exercise. And hope you can follow me when I'm talking about this. Any questions? Okay, so try to think about that at home, okay? Now here I try to remind you again, right? I try to remind you again, what is the potential versus electron potential? And so-called electron potential is what we do in band diagram, right? So electron potential, electrostatic potential is just phi, right? But the potential, okay, my connection was not good, right? Can you hear me now? The potential is phi, right? Potential seen by the electron. Right? Or the potential when the electron is there is negative Q times phi. So it is negative. Can you hear me now?
Yes.
Okay, right. So that's why earlier when we have a potential going up, then this is going down. This is for band diagram. Because for band diagram, we only care about the electron, how the electron feel. Okay, just a concept I want to remind, is everyone okay with that? Just like here, we use Poisson equation to derive potential. But when you go to band diagram, you flip it. It means the electron want to go to this lower part, right? Want to come to here. But it means higher potential, which is correct. Electron want to go to a more positive potential, right?